People think there would be no class today.
I don't know.
Someone asked on the Discord if there's class today.
Oh, really?
I'm like, yeah, of course there's class today.
I think it's funny how people ask questions that are like, you really should know this. Like,
Yeah, I know. I'm wondering if I said something that made it seem like there wasn't class today.
I didn't think so.
It is midterms week, so I know everyone's busy.
I forget. Did you say you were going to post the solutions to homework 3 today?
It's posted, so
Oh,
it's,
okay.
it's on Canvas.
Thank you.
Yeah. Send out an email with the solutions and also a link to the review video too.
Oh, yes, I did see that.
Right, it's 8:30, it's going to get started. Good morning, everyone. How's everyone doing this week? Doing all right, it's midterms week, so I know it's I'm sure you guys are, really busy studying and stressed, so I know this is an early morning class, so just want to say thank you guys for coming out. I'm contractually obligated to be here, but I know you guys have a choice, especially when the lectures are recorded. So thank you for coming. Okay, so we have an interesting week this week. So Thursday, of course, is our midterm exam. Remember that midterm exam is going to be in person, so please plan to be here on Thursday. Right? Remember, you can bring a cheat sheet, you can bring a writing utensil, you can bring a calculator, right? Yesterday I recorded and I posted the review video, so you guys should be able to access that now. Okay, if you didn't get that email, just let me know. The review video is about an hour long, and I covered basically everything that we've gone over, right? So for the review video, you'll see if you haven't watched it yet, I focused mostly on just kind of how to do all the different problems that we've gone over, and we've gone over a lot. But I didn't cover a lot of the conceptual information, and so make sure that you're studying that on the study guide, because you're going to need it for the week. Okay, and then for today, we're starting something new. So today's lecture is not going to be on the midterm. So this is going to be, for the future. And since this is kind of a busy week, I thought I'd do today it's not that bad. So we're mostly reviewing just vector algebra, a little bit of vector calculus. So you've probably seen a lot of this before in your previous classes. But we're reviewing it just to kind of set the table for where we're going to go over the next step. All right. Are there any questions about the midterm or about anything that I can answer right now? Okay. All right. So I will say that I'm you guys may not be happy, but I'm very happy to see you guys today. Not only because it's midterms week, but I almost died over the weekend. My good friend, he's getting married next month, so he wanted to go snowboarding for his bachelor trip. The problem is there's huge blizzards going on up in the mountains right now. So we went up to Mammoth, we went up the lift, we went to the very top of the mountain, and it took us almost 4 hours to get down the mountain because the blizzard was so thick. So, and we lost some gear. I lost my helmet, I lost my glove. There were times where I thought, I'd never see my wife again, never see my family, but we made it. So, happy to be here, happy to see you guys. Okay, all right, so let's go ahead and get started for today. And so, the theme for the next few weeks, so we're actually taking a very different direction in the classes. So, for the first 6 weeks of this class, we focused purely on differential equations, right? So we did a review of kind of the classical way of solving differential equations, and then we learned about Laplace transforms, which is kind of an alternative. Right? The thing about this class 308 is we're kind of in a weird spot because basically what 308, the reason it exists is that we have to cover a lot of different math concepts that you need for your future courses, for your upper division courses. And so it's really just kind of a cornucopia of different math stuff that may not have anything to do with each other. And so we're going in a completely different direction today. So definitely remember about differential equations for the midterm, but that's probably the last time you're going to see differential equations in this class. Okay? And so for the next couple of weeks, we're focusing mostly on basically vector calculus. Okay? Okay. And so of course, vector calculus was covered before. So you've probably taken you've taken 3 calculus classes up to this point, 150A, B, 250A. Okay. And so we're not going to really, hopefully we're not going to learn anything totally new, okay? And in fact, we're not really going to be spending a lot of time on vector calculus at all. Okay? The motivation for this part of the class is that as you get into your upper division courses, think courses like fluid mechanics that you may have taken last semester, heat transfer, vibrations, things like that. You're going to be seeing a lot of equations that have these kind of vector calculus terms in them. Okay, and so kind of the goal for the next couple of weeks is to take these very common things like gradient, things like divergence, line integral, surface integrals, and I really want you guys to have not really learn how to compute these, but more just what are their physical intuitions and how can you kind of better understand them? Because when you see these in your future courses, or maybe you've seen them already, they may as well just be another language. But all of these operations, they have a physical meaning, and it's important to know them to kind of get a better understanding of your other courses. Okay. And so what I'm hoping is that you've seen a lot of these operators before in your previous classes. But when you learn about these operators in like a math class, it's a little bit different than learning about it in an engineering class, right? And so when you're learning about it in engineering, these mathematical operators have a physical meaning, right? So they relate very closely to a physical phenomenon that you can observe. So what I want to do in the next couple of weeks, and it's not a lot of time, right? It's not a lot of time to cover a lot of vector calculus, but we're going to go over each of the main operators and just mainly talk about what they mean and how they're used in engineering practice. Okay, but before we can get there, we're not able to get there yet. Today, what I mostly wanted to focus on is just a review of vector, not even vector calculus, but vector algebra, right? So defining what a vector is, what a scalar is, what a field is, dot products, cross products, okay? So a lot of things that hopefully I'll review. But again, it's the midterm week, so I didn't want to do anything too heavy or too conceptually, too. Okay. All right. So first, let me start by saying that up until this point in the class, we've mostly focused on functions that only have one independent variable. And so a lot of times this was distance, and so this would be the x variable, or more recently we've been using time, t. So that's always a good place to start. And so even in calculus, you start with single variable calculus, or you go to multivariable. But in general, most phenomenon, especially in engineering systems, are multivariate. So they're going to be functions of multiple space variables x, y, and z, or they could be functions of space and time x, y, z, and t. So let me just give you a couple examples just to kind of illustrate this, right? And so if you're into structural engineering, whether you're mechanical engineer or civil engineer, you're designing buildings and stuff. And so a lot of times you're interested in stress analysis. And so for instance, let's say that we have a two-dimensional object. Okay. So let's say it's a plate. Okay. And let's say there's a big hole in the plate. And if you take this plate and you pull it on both sides, you basically apply equal and opposite force on both sides. So statically, the plate is staying still, right? But you know that, if you take any object and you kind of pull on it and you kind of, pull it in tension, then inside the object, there's going to be some mechanical stresses. You might see something where like, maybe this area right here, around the hole, this might be high stress. Here, you might have lower stresses. And so in this situation, if what we're interested in is, how the stress is distributed, the stress is a function of X and Y, right? So it's because it varies in two dimensions. Okay. And so mathematically, we usually denote that as sigma, and then, we give it two variables there, so X comma Y. Okay. So that tells us that our stress depends on both the horizontal distance and the vertical distance. Or maybe you're an electrical engineer, or maybe you're a mechanical engineer working on computer parts. Okay. One thing that you're always concerned about when you're designing computer systems is cooling. So, you may be interested in this. So let's say that you have like maybe a computer component. Okay. Also in the shape of a rectangle, because my artistic skills are extremely limited. Okay, so use your imagination, right? So imagine there's a lot of electrical component on here. So they're like chips and stuff. Okay. And as you know, if you've ever, designed a computer before, or if you've ever, looked inside a computer, these components get pretty hot, right? And so as they're computing, as they're running, they're producing heat, and that heat is going to be, distributed to them. You might have some regions that are maybe hot, okay? Maybe where the processors are, or the graphics card is. And you're going to have some regions that are cool, okay? And so in this situation, we have our temperature. Temperature is our variable of interest. Okay. And again, it's a function of X and Y. Okay. And so the reason I bring up these situations is that because of their multidimensional nature, you can't just use a single variable function to describe its behavior, right? You need multiple dimensions. You need multiple dimensions. So what you'll see is that, a lot of engineering, especially, more complex analysis, they rely on these kind of multivariable functions in order to perform the analysis. Otherwise, it's just impossible. Okay. All right, any questions on this so far? All right, so I'm going to give a different term for these multidimensional functions. Okay. So typically in engineering, when you have a function here that depends on more than one space variable, so either X and Y or XYZ or YZ or something like that, we typically call those a field. And so field is an engineering quantity of interest that depends on more than one space variable. Okay. And so, by the way, when I refer to space variables, I mean kind of the different kind of Cartesian coordinates usually. Okay, so x, y, z. You can have different space variables as well. Like if you have cylindrical coordinates, you can have r, theta, and z. Okay, or even spherical coordinates too. You can have r, theta, and phi, which are the angles. Okay, but most of the time, just because it's a lot simpler, at least for now, we're going to stick to Cartesian coordinates. Okay. All right. And so the two examples that we did above are examples of fields. And so we have a stress field and we have a temperature field. Okay. So when people say field, that's typically what they mean. And so there's two types of fields that we typically use in engineering. So the first is a scalar field. Okay. And so a scalar field is just a single function, basically. Okay. So basically, it associates a scalar value to every physical point in space. Okay. So something like a temperature field, that would be a scalar field because temperature is a scalar. We also have vector fields. And so a vector field associates a vector quantity with every point in space. So an example of this that you'll see fairly often. This comes up a lot in fluid mechanics, and so if you've taken fluids, you took fluids last semester, you probably are familiar with the concept of a velocity field. So vector fields are interesting because I think this is where people kind of get intimidated, right? So we know a vector has more than one component, right? So vectors are either two components in 2D or three components in 3D. Okay? When you talk about a vector field, each of those components can depend on each of the spatial coordinates, right? So I'll give you an example. So in 2D, we have two velocity components. We have u and v, where u is the horizontal velocity and v is the vertical velocity. Okay? When you talk about the velocity field in 2D, each of these components are functions of x and y. So u of x and y and v of x and y. Okay? And together, these two make our velocity field. Okay? So that's how you usually see it denoted. So you have a vector v that denotes velocity. That is a function of x and y. And then each of its components, u and v, are also a function of x. In 3D, it gets even more complex. In 3D, of course, we have three components of velocity. We also have three spatial variables as well. U, function x, y, and z, v, function x, y, and z, and w. So if you haven't seen w before, w is the component of velocity in the z direction. And so it looks something like that. Okay. So vector fields, even for people who have been doing this for many years, vector fields are not fun to work with because you're basically doing like either 2 times the work or 3 times the work. Okay. And it gets even more complicated because in the equations themselves, the different components are going to interact with each other within the equation. So it gets very complicated very quickly. But you know, we'll definitely cover that you know, once we get there. All right, so those are our two types of fields, okay? And so you know these are kind of important to understand, especially in terms of you know how we actually use them. Okay, any questions on this? Okay. All right, so fields, you know, fields are an important concept that we're going to use. Okay? A field again is just basically just a multivariable function. And so we're going to be performing operations on these fields, mostly calculus operations. But before we can get to those kind of vector calculus operations, we have to kind of review a little bit of vector algebra. Four. Vector algebra really kind of forms the basis of you know of how to work with multivariable functions. Okay. And so you know we're going to cover the basics first, and then you know we'll see how those apply later on. Because when we get to the more advanced operations like the gradient and the curl and the divergence and line integrals, surface integrals, you know, all those are built on kind of an understanding of vector algebra. Okay. So let's just review those kind of fairly quickly, and we'll you know, and then we'll go from there. Okay. All right, so first let's define a vector. It's, you know, like I mentioned earlier this semester, this is probably the first time in 4 years I've taught this class. I used to use the joke here. I don't know if people still understand this, but there was a movie called Despicable Me that came out when I think probably when I was in college or high school. And there was a villain in there named Vector, and his kind of catchphrase was that he did evil with direction and magnitudes. That's why I've always kind of remembered that as Vector. But you know, I don't know if people don't watch Despicable Me anymore. Okay. So a vector is basically a quantity that has both magnitude and direction. And so visually, you know, we usually represent vectors with an arrow. Like this. Okay. And so the magnitude of the vector is usually denoted by the length of the line. This length right here usually is the magnitude. Okay. And the direction is denoted in terms of, you know, which direction it's pointing. So there's lots of different ways that you can quantify the magnitude or the direction. And so kind of the simplest way is to use an angle. Okay. And so if you draw an angle here and you kind of define the direction of the vector with respect to, you know, its angle, okay, that's one way. It's kind of like a polar coordinate way to describe the direction of a vector. Okay. But I think the more common way is to basically define a vector by its components. So vector v, 2D at least, is given by Vx and Vy. Okay. And then depending on the ratio or depending on the relationship between Vx and Vy, that gives you the direction of that vector. Okay. But I think the component form is a little bit more. All right. So that's a vector, okay? Vectors are used to represent a lot of engineering quantities. So we've already talked about velocity, but we also represents things like displacement, okay? Even more uncommon things. And so, probably next year you guys will be taking heat transfer. And so there will be things like the heat flux or the heat transfer rate that's represented by vector. Even if you talk about electromagnetism, the magnetic field or the electric field, that's represented by vectors as well. Okay? So vectors and engineering kind of go hand in hand. You can't really do any kind of engineering analysis without vectors. And so there's a lot of things you can do with vectors. You can add vectors together. And so when you add two vectors together, the way that you do it is you just add their respective components. And so, you take two vectors, first of all, they have to be the same size. And then you match up the components that are in the same slot and you just add those together. And so if you have a vector A, A1, A2, A3, and a vector B, B1, B2, B3. We can define a new vector C. So the result of a vector addition is another vector. Okay? And so when you add A and B together, you get a new vector C. And its components look like the following. So we have A1 plus B1, because those are the two, that's the first component of both of the vectors A and B. Okay, so we're going to add those together. Then we have A2 plus B2, and then A3 plus B3. So pretty simple. So hopefully everyone's seen vector addition before. We can also multiply a vector by a scalar. Okay, so we'll call this scalar multiplication. And so when you multiply a vector by a scalar, so you basically multiply by number, you multiply that number to each of the components. And so we have a vector A. We multiply it by a scalar, so we'll call the scalar K. So Ka. Right, the result of this is going to be K times A1, A times A2, A times A. And so, the scalar just goes to all three components, okay? Maybe one wrinkle to this, or maybe one other interpretation of the scalar multiplication, is that we often use this to increase or decrease the magnitude of the vector. Because there's a lot of times where you want to change the magnitude of a vector to make it either easier to work with or more difficult to work with. Okay. One very common example that happens a lot in engineering is what we call normalizing a vector. Okay? And so what that basically means is that we modify the magnitude of the vector so that it has a magnitude of 1. Okay, we preserve its direction, so we still have the vector point in the same direction. We just want to make sure that it has a magnitude. Okay. And so if we have a vector A, right, we can compute the magnitude of A. Maybe I should have listed this earlier, but the magnitude of a vector is you take the square root of each component squared added together. So that's the magnitude of a vector. When you compute the magnitude of a vector, the magnitude of a vector itself is a scalar. Right? And so what we can do is we can divide, we can do scalar multiplication, we can also do scalar division. If we divide a vector by its magnitude, then its new magnitude will be 1. Okay? And so oftentimes what we'll do is that we'll define, we'll say we'll do basically 1 over the magnitude multiplied by A. And so what this is going to be, following a formula from above, we have A1 divided by magnitude of A, okay? A2 divided by magnitude of A, and A3 divided by magnitude of A. Okay. Right, so those are our 3 new components. And so this vector itself is going to have a magnitude of 1. Okay, so what you'll see often, or at least this is the notation that I use, is that when you have a unit vector like this, and so a unit vector is 1 with the magnitude of 1, we usually give it a hat. That's what we say, this is a hat. Okay. And so that little kind of triangular hat right there basically says that it's a magnitude of 1. The way I always remember this is that the hat always looks like a kind of like a birthday hat to me, and so it's like this. It's like when you turn 1 for the first time, right? So you have your first birthday, you put a hat on, and so it's like this vector has a magnitude of 1, so it's like it has a birthday. It's my own weird way of looking at it. Okay, any questions on this so far? All right, next thing we're going to review, let's review IJK notation. And so IJK notation is just a different way to represent a vector. Okay, so up to this point, I've been using, I guess, component notation. And so component notation lists the different components in a parentheses separated by commas, but IJK notation represented in a different way. As an example, let's have our usual vector A, so A1, A2, A3. Okay. So that's how we've been representing it, right? So our three components within parentheses separated by commas. Another way you can represent this is you can have A1 multiplied by I hat plus A2 multiplied by J hat plus A3 multiplied by K hat. Okay. So you'll see this notation sometimes as well. And so some faculty kind of prefer this notation when they're writing vectors. Okay. And so the reason this notation works is it's kind of a combination of the two previous exercises that we did. Okay. So I hat is simply just a unit vector in the x direction. Okay. And so it looks like just this. Okay. It seems ironic that we're using component form to define the IJK notation, but that's kind of how we roll. So this J hat is the unit vector in the y direction, and so this is going to be 0, 1, 0. Okay. And this K hat is then a unit vector in the z direction, 0, 0. And so if you add all of these together, so this is basically a sum of three different vectors. Okay? Basically, what we're adding together is A1, 0, 0, plus A2, or excuse me, it's going to be 0, comma A2, comma 0, plus 0, comma 0, comma A3. And so if we add all these three vectors together, we get a single vector A1, comma A2, comma A3. So sometimes you'll see this notation. I would say it's more kind of an old school thing. So, for me, for myself, when I was in college, it was mostly the older faculty that did this. But, everyone kind of represents vectors based on how they were trained. So, if you see this, don't get confused. It's still a vector. It's still a single vector. It's just that you add them together like that. Okay. So that's IJK notation. Let's start reviewing some vector operations. So let's start with the dot product. So a dot product is a very important vector operation. And basically, when you take the dot product between two vectors, kind of the most important thing to remember with the dot product, the equation for the dot product, of course, is important to remember. But the bigger picture thing is that when you take the dot product between two vectors, you get a scalar out of it. Okay? So a dot product is a vector operation. Okay. The dot product is a vector operation that gives you a scalar. Okay. All right, so it looks like the following. And so if we have two vectors, A and B, and so if we take the dot product between the two vectors, A dot B, the way that we do this is that we multiply each of the matching components together and then just add them all up. Okay? So this is going to be equal to A1, B1, plus A2, B2, plus A3. Okay. And so this, everything here, when you add it all up together, you don't get a vector anymore, you get a scalar. And I remember when I first learned dot products and my math teacher was telling me this, it seemed like such an insignificant thing. It's like, who cares if you get a scalar from two vectors, right? That's just how the operation is defined. But that's actually, a really useful thing that's used a lot in engineering. Okay. All right, so some examples of the dot product being used in practice. You may have seen these before. Right, so some applications that you've done is maybe computing the work done by a constant force. Or more importantly, there's a geometric application as well that we'll go over, which is which is determining if two vectors are orthogonal to each other or perpendicular. So let's dive into that second application real quick. Okay. And so the dot product actually has another formula. Okay, so I would say this top formula here, that's how you actually compute the dot product, but this is actually equal to something else as well. Okay. And so the dot product, we're not going to prove this, although you've probably seen the proof before in a previous math class. The dot product is basically equal to the product of the magnitudes of the two vectors. Okay. And so magnitude of A times magnitude of B multiplied by cosine of whereas theta, this theta here is the angle in between the two vectors. So we have two vectors here. This is vector A, vector B. Assuming that they're not the same, okay. And so when you have two vectors that are pointing in different directions, there's always going to be an angle in between them. Okay. And so a way that you can find out that angle is through dot product. And so with that said, you can take this equation and solve it for theta. And so you do that, you get theta is equal to cosine inverse of product A dot B divided by magnitude of A, magnitude of And so determining the relative orientation of two vectors, I would say this is one of the more common applications of the dot product. Any questions on this? Okay. All right. And so of course there's a special case for when the dot product between two vectors is 0. Okay. That means that the angle in between these two vectors has to be 90 degrees. Or pi over 2 if you're into radians. All right, and we can see that very simply from this equation right here, right? And so if you look at our equation for theta, so we know theta is equal to cosine inverse of A dot B divided by magnitude of A, magnitude of B. if the numerator of this expression here, the a dot b, if that's equal to 0, then essentially what we're doing is we're taking cosine inverse of 0. And so taking cosine inverse of 0 is like saying the same thing as cosine of what angle gives us 0. And so there's only one, well, there's, I guess there's infinitely many, but between 0 and 180 degrees, there's only one angle that gives us cosine of 0, okay, and that is 90 degrees. All right. So I think that's about it for the dot product. So the important things for the dot product are first of all just the formula that we use to compute it. We're going to use that actually together with some calculus probably next week, and also kind of this property here with determining the angle between the two vectors. Okay. Any questions on dot product? Okay. All right. So let's go ahead and move on to the cross product. So the cross product is another vector operation. You've probably seen it before. But the result of a cross product, when you take a cross product between two vectors, is another vector. And so cross product is denoted by, an X. And so we take the cross product of two vectors, that gives a third vector or another vector B. So that's the notation that we use for the cross product. The most important aspect of the cross product is the fact that the new vector that you get is orthogonal or perpendicular to both of the input vectors. And so that's really useful when you when you want to find a vector that's perpendicular to two. And so the cross product kind of does this automatically. So to compute the cross product, I think there are multiple ways to do it. But the way I usually like to compute the cross product is I use kind of a pseudo matrix. And so if we take A cross B, what I like to do is I like to form this kind of 3x3 matrix, and then take kind of selective determinants of that. Okay. And so in the first row of the matrix, we're actually going to have our unit vectors in each of the directions. We have I hat, J hat, and K hat. And then the second row of the matrix is going to be the components of the first vector. Okay. So since our first vector here is A, we have A1, A2, A3, and the last row is going to be B1, B2, B. Okay. So now let's take the determinant of this to determine its cross product. Okay. Okay. So if you've never taken a determinant of a 3x3 matrix, the way it usually works is that you basically, you start from the first row and you go term by term in the first row. And so let's say we start with I hat here. What you're going to do is you're going to block out the row in the column for that for that component. And so our first term of the cross product here is going to be I hat. Okay. And you'll notice that when we block out the first row and the first column, all we're left with here is this kind of 2x2 matrix down here. So we're going to have I hat multiplied by determinant of A2, A3, B2, and B. And so practically, I think when you're computing this by hand, what I like to do is I like to just cover them with my fingers, and then I just kind of see what's left, and that gives me the the new 2x2 determinant that I have to do. It's a little bit hard to kind of show that on the iPad here, just because I know people in the class can see me when I go up to the board, but then on Zoom you can't really see. So I'll kind of do this one at a time. With this right here, this is a 2x2 determinant. Of that description ended up being a lot longer than I thought, but basically you block out the first row and first column, and just whatever's left, that's what you do. Okay. Go ahead and erase these. All right, so then we come to the second term. So the second term is going to be a minus term, and so make sure you do that. Okay. The next term is going to be j hat. We're going to have j hat over here. And just like we did with the first term, we're going to cross out everything that shares the row and the column with that j hat. So we're going to cross out, to the left and right, as well as directly below it. And then what we're left with is A1, A3, B1, B3, determinant. Don't forget this minus sign. I think this is the thing that's most commonly forgotten, when you're taking the cross product, is that second term you have to do a negative. Okay. And then of course we have to do this for k as well. So let me go ahead and erase this one more time. Okay. So k, we're going to cross out this row, this column. We get the determinant of A1, A2, B1, B2 times k. Right, and so from here, we have three components of the vector and three 2x2 determinants. Okay? So computing a 2x2 determinant is a lot easier, because all you have to do is you just multiply across the main diagonal, and you subtract the product of the off diagonal. Okay? And so we end up with the following formula. And so I know people that just when they think of the cross product, they don't do this kind of weird matrix thing. They just straight up memorize this formula. Which is crazy to me, because this formula is crazy. But if you end up doing that determinant, you end up with the following: you get A2, B3 minus B2, A3, I hat minus A1, B3 minus A3, B1, J hat plus A1 B2 minus A2 B1 A. So that's just a review of how to compute the cross product. Any questions on this? Okay. All right, so let's go over the right hand rule. So the right hand rule is basically a way, or it's a little trick that you can use to determine in which direction the cross product points. Because when you have two vectors, there's actually two different, you take the cross product between them, there's actually two different directions that the vector can point, right? The only requirement that we've stated so far is that the new vector be perpendicular to both of the component vectors, right? And so if you have a vector A and a vector B, okay, the third vector, the cross product, is going to be perpendicular to both of these, okay? But there's two options, right? So the vector could either be pointing out of the page, okay, so become pointing out towards you. And so that would be one valid vector that is perpendicular to both, okay? Or the other direction is that the vector is pointing into the page. Okay. So both are technically valid. So both satisfy the property that it's perpendicular to both. Okay. Right. And so of course, the cross product has to give you a deterministic result, right? It's not something that's just random. You can't flip a coin every time you check the cross product. And so there has to be some kind of convention to determine which direction the cross product goes. And so the convention that we chose, just I guess based on whoever invented the cross product was right-handed. Okay? We use the right-hand rule. Okay? And so it works like this. This is going to be very difficult to show because half the people are on Zoom. But let me describe it in words first. Okay. So using your right hand. Right, first thing you're going to do, and so let's say that you're taking A cross B. Okay. The order is important because the cross product, it's if you swap the order of the cross product to do B cross A, it's not going to give you the same result. Okay. And so for the first vector in the cross product, what you want to do is that you want to point your right thumb in that direction. Okay. And so this is vector A in our example here. Okay. Then, for the second vector in the cross product, for the second vector in the cross product, you're going to point your pointer finger in that direction. So this is B, our B vector. So thumb in the direction of the first vector, pointer in the direction of the second vector, okay? Then what you can do is you can curl your remaining fingers, so your middle finger, your ring finger, and your pinky, okay, such that it's perpendicular to both. Okay? I should say the direction. So the direction of the remaining fingers points in the direction of the cross. Yeah. Right, so let's try using the right-hand rule on this. Okay? And so if I point my thumb finger in the direction of A, right? So we point our thumb in the direction of A, our pointer goes in the direction of B. Okay. The rest of my fingers are pointing into the page, right? And so I'll show here for in the class, right? So my thumb, direction of A, pointer in the direction of B, the rest of my fingers go into the page. And so the result of this cross product is going to go into the page. Okay. All right, any questions on this? All right, so that was that was basically a lightning round of a vector algebra review. Okay, so hopefully that was useful. Hopefully, kind of it jogged your memory. Okay. But these are kind of the basic building blocks, and so these are all kind of operators that you've hopefully learned before. So now we're going to use these to define kind of more advanced vector calculus operations. Okay. All right, so for the last 15 minutes today, for the last 10 minutes, I want to let's go back to fields. Okay. And so fields, like we mentioned before, a field is nothing more than just a multivariable function. And the way that we display fields, or the way that you actually view them, oftentimes is a bit different. So I think we're used to plotting one-dimensional functions, but when you're plotting fields, you're plotting it in 2 dimensions. Okay? And so usually, like if you have access to a computer, a field is often represented as a color contour, plot. But for example, and I'm going to bring back this example next week as well. Okay, when you're looking at a map of a particular area, right? One thing that you are often interested in. So let's say that you're hiking up in the mountains. Okay, hopefully there's no blizzard going on when you're hiking in the mountains. One thing you might be interested in is the relative heights of the area. Okay? And so to view this, you would look at a topology map. So let's say we have a rectangle here. And so what you'll usually see on a topology map is you might see kind of like, rings that kind of look like. Okay. And then the colors on the map will indicate to you how high each part is, right? So maybe you'll have this part here is red. Maybe this part here is orange. Yellow. Well. Okay. So basically, the colors tell you what, okay? Because when you're plotting in 2 dimensions, you can't use height of a line to determine a function value, right? So you have to rely on something else. And so colors are often. Okay. So if your objective is just to visualize a field, a color contour plot always does a pretty good job. Okay. But if you actually wanted to perform any kind of calculations, a color contour plot actually isn't that useful because the colors, you might have a color bar over here. Okay, that's usually how it goes. So either a legend or a color bar. Okay. If you want to do any kind of calculations off a color contour plot, it can be a bit different. When you get into multiple dimensions, like thinking about good ways to visualize your data actually is actually a challenge. It's something that people think. Okay. Another way that you can view results. So let's say for a vector field. A vector field can often be displayed as a field of arrows. And so let's do a interesting case. So let's say we have a disk that's spinning. Okay. And so the disk is kind of rotating around just like that. And so if you plot the velocity field on this spinning disk, okay, so let's say it's rotating this way, what you'll see is that you're going to have a much higher velocity magnitude at the edges compared to the And so instead of using colors to display the field, you basically have these vectors that go there as well. Okay. And so these vectors, their advantage is that they can display, magnitude and direction. And so that's how you display that. The downsides of using an arrow field, I've seen them used before to display data. They're not the most visually appealing, right? And so you have the color contour fields. At least you can use color there to denote the different different spaces. When you look at a bunch of tiny arrows, it sometimes can be a bit hard to follow. And it kind of had the same issue as before, where it's really hard to come across. All right, any questions on this? Okay, all right, so let's stop it here for today. We'll stop a little bit early. And so when we come back next Tuesday, we're gonna start to get into the calculus part. And so we're gonna talk about things like gradient, like the divergence, like the curl. Okay? And we'll see all the vector algebra stuff that we've had today. All right, so next time I see you guys will be Thursday for the midterm. So remember, midterm is going to be in person, so please come. I can't emphasize that enough because every semester someone stays home and they forget or they expect that midterms on Zoom. So there's no Zoom midterm, so you have to come here. Okay. Remember, you don't have to print out the Laplace transform tables. I'll give that to you. Just bring your cheat sheet, your writing utensil, and your calculator. All right, so best of luck studying, everyone. Make sure you check out the midterm review video if you haven't already. Solutions to homework 3 are posted as well, so you can check that out. And if you have any other questions before the midterm, always email me. And I have office hours on Wednesday before the midterm. Okay. So best of luck studying, and I'll see you guys all on Thursday.
Yeah.
I will give you the table. I'll give you the derivative. Yeah, so that's actually usually one. That would be one, right? It's a little bit redundant, and so when you have to go but it is, but the solution comes out. So if you leave it out, that's fine. But I just put it there just to be consistent. I mean, it is cool. I didn't study, so like you just carry out extra.
Yeah. I'm hoping this is good. Static stuff. But I only saw one example of that. Its likelihood is give you that. Probably. What?
Yeah. I have to check and see. It might have been a mistake. It might have been a typo on mine. But everything else looks.
Trust the process.
My cheat sheet, but yeah, follow the process. Well, I'll check my work again. Yeah.
Okay, we ball. Really?
Yeah.
So isn't it like past midterm?
No. So the homeworks, I gave you really long part so that because you have a lot more time with homework. With the exams, you only have 75 minutes. And so the math is going to be a lot. So my policy is always that homework earlier here.
Yeah, that's why I was thinking not in 10 minutes.
You have just a lot less time.
On time.
Oh, yeah, no, for sure, guys. Time will not be. Will not be an issue.
That's crazy. I haven't got it.
No, that's either way, like a month. That's fine, yeah, you can still turn it in. I mean, just, if you don't look at them before, no, that's fine, yeah.
Do you remember how to do the fact that it's a key problem?
If we do, are there any final questions before I close it up? Are you guys giving me? Right? It's different. All right, I'll see you Thursday. Either gonna be